All right, this is Physics 1B for October 12th, and we're going to talk about molar heat capacities of gases today and try to gain some understanding about this 3/2 number that we had derived in the previous class. And then we're going to spend the majority of today's class just talking about the exam. This will be a shorter lecture day than normal. So just as a kind of a matter of review, one of the things we derived last time is this first equation right here, and I think I have it pulled up to where I can just pop to it. We spent quite a bit of time going through a derivation. I don't know if you remember this, but we wanted to understand how an ideal gas works, and we treated the ideal gas as made of a bunch of particles, and we made some arguments about what the pressure would be. And we said the pressure is related to the force is related to the change of momentum, and then we just kind of basically counted up how many molecules in here were moving to the left and would then strike the wall to produce a pressure. And through that derivation, we eventually came to this really simple result right here, that the translational kinetic energy of a gas is equal to 3/2 times the number of moles times the gas constant times the temperature, giving a direct connection between kinetic energy and temperature, which is really powerful. The idea that the temperature of an object is related to the average kinetic energy of the gas. And one of the kind of key things that we did, and we discussed this last time, but just to remind you, it was a week ago, was we made this assumption that the velocity of the molecules in the x direction, the y direction, and the z direction, if you were to average them and square them, that these should all be kind of equal to each other. The idea that basically the velocities kind of, you can split into three. And that's where this 3 number came from, and then why it showed up in this equation here. So what we're going to do today is we're going to connect that to molar specific heat. So going back much earlier in this chapter, perhaps the last chapter, I think, when we talked about specific heat, we derived this equation here, where we said that there's kind of 2 different kinds of specific heat. If you remember, there was the kind where we said Q is equal to mass times specific heat multiplied by change in temperature, right? And of course, to relate it to the equation that's written right here, you could write that as like dq was equal to m times c times dt. There's really not much of a difference between these 2 expressions, to be honest. It's the delta versus the dt. Just that, you guys have some calculus things you can do when you have these dt's that show up, right? But then there was another version that looked like this right here, wherein, how do you get to it, I guess? The number of moles, right? If you multiply that times the molar mass, right? This gives you the mass, right? Is that right? So that the dq would become N times molar mass times specific heat times dt. Okay, and I didn't look this back up, but then I think that this quantity here ends up being what we call CV, the molar specific heat. And what's remarkable is if you look at this table right here, for monatomic gases, you get pretty much the same number for this molar specific heat. This would be molar mass times the specific heat of the gas. Now, obviously, these gases don't have the same specific heats, C, but their what's called the molar heat capacity does end up being really similar. And what you notice is that between monatomic and diatomic molecules, you get different values, but that for the diatomic molecules, see, it's like 20, 20.7. It's all around 20, right? And so we want to kind of have an understanding of where these numbers are coming from. And so what we can do is we can say that when you add heat to a system, the dq is, you're adding heat, right? It can have the effect of changing temperature, right? And what we learned last time is there's a connection between temperature and kinetic energy. So it must be the case that we can kind of equate these 2 guys, dq and the translational kinetic energy, and that leads us to this equation right here. But then if you look at the equation, you got a number of moles on both sides that cancels, dt that cancels, and really what you're left with is 3/2 R is equal to CV. Okay, so this tells us that the molar heat capacity at constant volume, that's what this represents, molar heat capacity at constant volume, for an ideal gas of specifically point particles, so things that are monatomic, that the molar specific heat the molar heat capacity, is equal to 3/2 times R. Just this really simple relationship right here, 3/2 multiplied by the gas constant. So we want to understand why is it 3/2? That's a very specific number. It's not 1.57, it's exactly 3/2. So why is that the case? So again, we can relate this back to what we did last time, and you can immediately see what it was. It was because the molecules, we discussed them as moving in 3 dimensions, right? So this leads us to something that's called the principle of equipartition of energy. Okay, this is something that this can actually be derived. What we're about to say here, this can be derived, and to some extent, we kind of went through a very kind of brief derivation of it last time. But let's read what this says right here. This is a really, really important theorem in physics, by the way. It gets used to describe stellar physics, like how stars work. We use it to describe how gases work. It's a theory that's really good when you have large number of molecules or large number of particles that are all moving randomly, okay? And you want to understand something about their properties. So it states that each velocity component, either linear or angular, has on average an associated kinetic energy per molecule of 1/2 kT, or 1/2 the product of the Boltzmann constant and the absolute temperature. The number of velocity components needed to describe the motion of a molecule completely is also referred to as the number of degrees of freedom. This is a really common thing that we use in physics to describe what a molecule can do. So a molecule that's moving in a 3-dimensional space, if it's a diatomic molecule, and we describe space with x, y, and z coordinates, any molecule is going to have a velocity, and that velocity is going to have components that are going to be vx times the I hat, vy times j hat, and vz times k hat. You need at least 3 numbers, vx, vy, vz, to describe the motion of an individual molecule. So we say that means that those 3 things lead to 3 degrees of freedom. Degrees of freedom. So for a monatomic gas, there's 3 degrees of freedom, and it gives a total average kinetic energy per molecule of 3/2 k times t, which is consistent with this equation, not this equation here, but the equation that we had derived last time, which was that the kinetic energy was equal to 3/2 kT per molecule, basically. Okay, so this is called the principle of equipartition of energy. And you can go read more about this if you want to, and you'll see that there's a lot of information on the internet about how this is a very useful type of way of thinking about gases as well as stars and things like this. Okay. Anyone have any questions? So what about these ones right here? What about the diatomic molecules? Why are they different? Do they maybe have more degrees of freedom? So let's, they have an extra one, Cam is saying. So look at these numbers right here. So what is R? R is about 8, right? So if you do 3/2 times 8, you get 12, yeah? And if you try to figure out what you would get for these ones right here, you're going to find out that the ratio is about 5/2. It's pretty easy to do. R is about 8, right? So if I take 5 times 8, that's 40 divided by 2. This is about 20, right? And R is actually like 8.3 or something, right? So it's a little bit more than this, but close enough, you get about 20. So then you have this 5/2 right here. And what Cam is saying is that for these diatomic molecules, they have extra degrees of freedom. If you go back to what we read, what it says right here, it says that each velocity component, either linear or angular, so these are linear, right? Just to remind you, linear means motion in a straight line, right? So you can describe motion in a straight line with these 3 components right here. But what if the molecule is diatomic? If the molecule is diatomic, and you've got, let's say like hydrogen, for example, so you've got an H molecule here and an H molecule here. Well, this molecule, it has the ability to spin, right? It could spin like this. And I can't draw it very well, but it could spin kind of coming out of the screen. You know what I mean? It could either spin on an axis the axis that comes out of the screen, or it could spin on an axis like this, where it would rotate like this. Now those look very similar to each other, but it's either rotating in the screen or it's kind of rotating out of the screen. I can't draw that particularly well, but I did kind of take these pictures from the book that helped to hopefully show what that looks like. I don't think I can get these all on the same screen, so we'll go through them one at a time. So this is the motions of a diatomic molecule. And we look at its center of mass, and the center of mass can be moving in the x direction, the y direction, or z direction. That gives us the 3 that shows up right here. But then we also have what Cam is saying, that there's rotational motion as well. The molecule rotates about its center of mass. This molecule has 2 independent axes of rotation. I don't know if this is better than the drawing I did, but the idea would be that if this is x and y, the molecule can either rotate around the y-axis or it can rotate around the z-axis. Is there another axis it could rotate on? So this counts as 3 degrees of freedom. This counts as 2 degrees of freedom. So what we get from these two is that the specific heat, the molar heat capacity, ends up being equal to 5/2 multiplied by the gas constant R. 3 plus 2 is 5. What about the other rotation? It could. What other axis could it rotate on here? It can rotate on the y-axis, the z-axis, or what other axis? The x-axis, right? Yeah, it could be rotating like this. Why don't we include that one? You have any ideas? Why isn't it 6 halves or 3R? Oh, I imagine that they're definitely rotating about this axis. I can't imagine anything that would stop them from doing so. I think they are probably rotating about this axis. Is it because the 2-point mass is relying along that axis? Maybe that has something to do with it, Kenny. What do y'all think? Okay, so just to start from the beginning again, we say that there's 3 degrees of freedom for translational motion. You can move in the x, y, and z direction. That's pretty clear. But we're only saying that there's 2 independent axes of rotation that affect the energy of the system. One of them is along the y-axis. One of them is along the z-axis, so that causes the particle to rotate in the plane of the page, right? Either M1 comes out towards you and then rotates back in like this. So why are we not including this rotation, which is certainly possible, right? The x-axis? Yeah. What do y'all think? Why are we not including that one? So are the other two. Y and Z are both rotational kinetic. Kenny, why would what you say matter? You said because the 2-point mass is relying along that axis. I'm not saying this to just deter you, but just to relate it to the moment. That's a word that I don't think everybody in here knows what that word means. What is the moment? Torque. That's a word people know. What about the torque? Why would it be negligible? Ah, see what Kenny just said? There's no perpendicular distance from the point masses to the x-axis because they're parallel to it. Yeah. I think that has a lot to do with it. So what your book says that there's no way to change this degree of freedom in a collision. So part of the way in which these molecules gain energy, right, is they collide with other molecules that are moving quickly. And you can certainly see how a molecule colliding with another molecule or a molecule colliding with a wall would easily alter any of these, right? Could change the direction that the particle's moving. Likewise, two particles bouncing off of each other, you could see how it might alter the rotation in this direction or the rotation this way. But what the book says is you can't alter this x rotation in a collision. That's what the book says. I like what Kenny said better, though, because that's personally the way that I was thinking about it, is that when you have an object and you want to think about its rotational kinetic energy is related to how far away these masses are from the axis of rotation, right? And there's certainly going to be some distance between where this center of mass of one piece of the molecule and the center itself is. There's going to be some distance there, which is going to lead to a decent amount of kinetic energy rotating about that axis. But there's going to be very, very little kinetic energy rotating about this x-axis, I think, is part of the reason why. That seem reasonable to y'all? I don't know. What do you think? Okay. It's kind of like the idea that if you think about a pencil, so take a pencil, you've all got hopefully a pencil or something sitting in front of you here, and you think about, okay, how hard is it to rotate the pencil like this versus how hard is it to rotate a pencil through an axis that goes through the board, and then think about how easy it is to rotate the pencil along the axis along its length, right? It's because what we say in physics 1A, the moment of inertia is smaller, or it just takes very little torque to actually rotate about this axis here, which I think is kind of consistent with this. Tom says, is that why the other ones have a slightly higher CV? I don't know. You're saying these two here have a slightly higher CV? It might be related to that. I don't know. Let's actually calculate this. If you do 5 halves times 8.31, what do you actually get? You're going to get another 5 times half. Half of 30 is 15 times 5 is 75. Is it 20.75? Is that what you get? A little higher than that, actually, probably, right? What is it? Can you guys calculate it? It's 20.775, so it's really close to 20.8. Huh. So hydrogen is the smallest, but then again, it's the simplest molecule. It could be the case that these are a little higher because of something like that. I don't know. Definitely shows you that what we're discussing here is not an exact statement, but merely something that's very, very close to the truth. Okay, there is one other possible degree of freedom, actually, and that is for vibrational motion. So if the bonds that are holding together our molecule here, and this is a molecule, are compressible in some way, then the molecules can oscillate in and out along those, kind of like as if there was a spring connecting them. And this would add at least one more degree of freedom for them to oscillate back and forth like this. And so what ends up really happening is that it's a little more complicated than we first described. This right here is a plot for hydrogen, and it describes the molar heat capacity as a function of temperature, because it turns out that this is actually a function of temperature. And over certain ranges, you get different values. So if you look at this graph, we'll just kind of look at it carefully. It says below 50 Kelvin, so this is very cold temperatures down here. The molecules undergo translation, but they do not rotate or vibrate. God, that sounds hard to believe. Doesn't that sound really hard to believe? That there's some temperature below which the molecules themselves just, they don't rotate? That just sounds really I'm really skeptical of that. No, rotating about their own center of mass. Anyway, that's what it says. And these are measured values at this point, right? Like you can go and you can measure. What would you be measuring? You'd be measuring this equation right here, dq equal to what is it number of moles here, right? So did I do this right up here? Mass is equal to n. Yeah, okay. All right, so this they're saying like for a given amount of heat that you add, what happens to the temperature change, basically, right? They're saying in this regime down here that your molar heat capacity is just 3/2 times R. But then once you get above 50K, appreciable rotational motion begins to occur. My guess is down here it's probably similar to something that you guys said. It could be that the rotational motions are negligible compared to the translational motions in this region. But then you have this region here, which is from about 250 Kelvin up to maybe 1,000 Kelvin. So this would be the more normal experimental range, right? Like in a laboratory, these are more closer to laboratory temperatures right here. And so at that point, the molar heat capacity is like 5/2 R. And then apparently what happens is that once you get above 600,000, the in and out motion of the molecules, the vibrational motion, starts to kick in, and you get another 2 degrees of freedom from that. So 5 degrees of freedom at normal temperatures, and then 7/2 or 7 degrees of freedom. Where's the other one coming from? So in and out is a vibrational motion, right? What would what's the other degree of freedom coming from? Because the claim would be that this is adding another 2 degrees of freedom, right? At least on what they're saying. How can we think of this as 2 degrees of freedom? Is it for each of the I guess maybe it's for each molecule. This one could vibrate and this one could vibrate, right? That's probably what it is. That seem reasonable? Okay. All right. Well, so that is molar heat capacity, and something you can look up in a table, or you can just remember that it's related to this quantity here, R times the number of degrees of freedom divided by 2. All right. So, are there any questions at all about this? Okay, the last thing that I want to do before we talk about the exam is I want to point you guys to this chapter right here. I don't particularly want to go through the math of this, but we mentioned last time when we were talking about gas molecules that we have these plots. I showed you some of these last time because we derived what's called the VRMS, right? The root mean square velocity for gas molecules. And I wanted to emphasize the idea that what that represents is something related to a statistical distribution of molecules. So not all the molecules have that velocity, but instead at different temperatures, the molecules have different peak velocities, but there can be molecules that have really high velocities, okay? What this curve represents right here is what's called the Maxwell-Boltzmann distribution function. So Maxwell is the same Maxwell, James Clerk Maxwell, who's known for work with electricity and magnetism. He also did some work in what's called statistical mechanics or thermodynamics. This peak right here represents what's called the most probable speed. And then the height of the peak is related to the number of molecules that actually have that velocity. Okay, and the thing is basically just that as the temperature goes up, you get more and more molecules out here at higher speeds, basically. Okay. So there's an explanation as to how you would measure the speeds with this device right here, and they go into some of the math. But the thing is, none of this gets derived. What they do is they basically just give you this. This is what's called the Maxwell-Boltzmann distribution function. It shows the distribution of the velocities of the particles, and you can kind of see the things that make it up. And so I figured we just talk about what the things that go into it are. So the mass of the molecule matters. You've got the Boltzmann constant, you've got the temperature. You've got velocity squared, that's the actual velocity of an individual molecule, and then the whole thing is multiplied by this thing right here. And if you look at what this thing is, it's mass times velocity squared over 2. What is that? mv squared over 2. What is that? It's kinetic energy, right? So really this is energy divided by kT. And k times t we found was directly related to kinetic energy, right? So another way to write it is just to replace the mv squareds with this E, which represents the translational kinetic energy of a single molecule. And then it gets written like this, which is a little bit easier to read, because then it's like the distribution is a function of the energy. But what is this curve going to look like? Because it's a when you plot it as the velocity, the function versus the temperature, well, it's going to look like these curves up here, basically. And you can do things like you can prove what we did before. You can prove that the RMS value is this. You can prove that the average value, if you want to, by doing what's set up here. To find average velocity, you basically take this function. You're welcome to do this yourself if you want to, and you perform this right here. You integrate from 0 to infinity velocity times the function, and that'll give you what's called the average velocity. How many people... Wait a minute. Who here's taking 1D right now? Anyone? Okay. So all I'm going to say is that what this represents is something called a probability distribution. The velocity of gas molecules is random, but it fits this distribution function. Some of the molecules are moving really fast. Some of the molecules are moving really slow. And the way that you actually get the average velocity right here, by taking the distribution function, multiplying by the velocity, and then integrating over all possible velocities. When you do take 1D, you're definitely going to see this stuff show up again. Except it's not going to be about just velocity distributions, it's going to be about position distributions. And the way that we do these calculations are very similar to the way in which you do calculations in quantum mechanics. So I'm just kind of mentioning that now, that this will come back. But personally, I think this is like a lot to digest as a student. Like if I was sitting there listening to this, I would just be like, what is this thing? And all I can say is that the book doesn't derive it, but it can be derived. Like this is something that can actually be derived from first principles. You have to take a class, or the class I learned about it in was called Statistical Mechanics, wherein you kind of go through and you derive all these things. But anyway, I'm just introducing this, just showing you this. I think personally, it is a lot easier to not have to worry about the math and just understand that when it comes to velocities of molecules, they have a distribution, and that distribution shifts to the right at higher velocities and higher temperatures, so that the peak velocity is shifted to the right. This to me is what you need to understand, is just kind of how this works right here. So do y'all have any questions? Molecules of gas have widely varying velocities. There's some average value that we can calculate. There's always this little tail that goes off to the right, meaning that some of the molecules move really fast, some of the molecules move really slow, but you shift the entire distribution to the right when the temperature increases. And that changes the average kinetic energy, etc. Okay. Baron, do you have a question? Okay. So, in that case, that's the end of this chapter. Because we have an exam coming up next week, and I'm not going to be testing on the next chapter. I feel like we have four chapters left in the textbook, and we have about 8 weeks to cover them. So, I think, should be easily able to do so without covering new material today, and that can give you time to prepare for the exam. So that's what I wanted to talk about for the rest of the class. In case anybody wasn't here last week, at the end of class, people started asking a lot of questions about the exam, and they're in the general chat if you want to see them, but I just want to make sure everybody's on board with what they can expect and give you the best opportunity to prepare for the exam next week. So these are the things that we're doing for the exam. I'm going to split the class in half. So we have something like 30 people in the class. So 15 people, will come Monday at this time. And then 15 on Wednesday at the normal class time. I'll give everybody about 10 minutes per person. And during that time, you're going to present a problem. That I assign to you. In advance. So you'll know, like one day, basically. So you have to present a homework problem that I assigned to you in advance, like in Discord, basically. Now, I don't know what kind of like tools you all have at your disposal. So you can either screen share. Oops. Like what I'm doing right here. Or you can work out what you've done and then take pictures of it. Okay. I would vastly prefer that you do this if you can. If you have any way at all to start from a blank piece of paper, basically, and then just start writing and explain every step, that's what I would prefer. If you don't have the ability to do that, then just take pictures of your work and explain it step by step. You could do this through, like, Paint if you want to. The problem is that, like, if you're in Paint... here, let me... So I could definitely use what I have, I think, in Paint, can't I? If I go to brushes or something like this, yeah. I could use this in just the same way, right? But it's exactly what Baron's saying. It's really hard to use with mouse. So if I wanted to write like 1/2 mv squared with a mouse, oh my god, it looks so bad, right? So I honestly, even if you want to suffer through doing this, I'll suffer through it with you. Because like as long as you make it thick enough, you can probably do it. It's just going to take, it'll be kind of like really slow and stuff like that. It looks okay-ish, right? I don't know. It's not wonderful. It's certainly not going to be great, but if you can do something like this, that's fine. If you have a tablet like I have, that's fine. If you don't, then don't worry about it. And just take pics of your work and then explain it step by step. I suspect this will be a very quick explanation, right? So, yeah. Let's see. So you're going to be evaluated based on... really not based on whether you got the answer right or wrong, but more just based on whether or not you use like kind of proper logic, reasoning, mathematics to get from beginning to end. So you're basically going to be evaluated. Do you want to explain the work on paper or when we are talking to you? What do you mean exactly, Andrew? Oh, do you mean on the piece of paper, should you have already written out the reasons and explanations? No. No, don't do that. I want you to use your words. That's a really good question, actually. Yeah, you don't need to include why you did something on each step. So that would be more like a mathematical proof, right? Where you'd be like, because of equation 18.31 or whatever, I would kind of prefer that you just explain as much as you can, and have kind of I would kind of prefer that if you're gonna take a pick of your work, that you've written the bare minimum that you need to get from step to step, and that what you're doing during that exam when you're talking to me is you fill in the gaps. Does that make sense? The conceptual gaps, so to speak, if they're there. So you're going to value based on clarity of work, the clarity of your explanation, and the accuracy of it, and then just general like knowledge of concepts that you show me. And I can kind of ask, yeah, is it like we're teaching you? Yeah. You're going to kind of treat me, that's a good way to put it. You're going to treat me like as if I'm a student and that I don't know anything, except that I do know the same like laws and rules, but I don't know how to do the problem. And you're just going to kind of explain it to me, it's like, explain it to me like I'm a student struggling with the problem or something like that. So like if you've ever tutored one of your friends, or if everyone's ever asked you like, oh, how did you do that, it's kind of the same thing. Just explain as much detail as you can, and yeah, I'll probably give you a score of like 1 to 10 based on how you did. Do you mind if you record your own presentation? That would probably be okay, as long as it was short. Like by short I mean 3 to 5 minutes would be long, but 3 to 5 minutes. And then, no, I really don't want you doing that. I want to interact with you. I want to be able to stop you and say, why is this? Why is that? Oh. Sure. Yeah, I mean, you can record whatever you want to. So, like, you mean, like, during the exam itself, can you record what's going on? Yeah, that's fine. Yeah. Totally fine. Okay, evaluate it based on clarity of work, explanation, general knowledge of concepts. I'm probably going to split you guys just using, what's it called? Your last name, most likely. So the first day will just be kind of like A through M or whatever, and then the next day will be M through Z, or however the split ends up working. But I'll let you know. So, like, if you're going to go on next Monday, what you can expect is I'll give you a, how am I going to do it? I guess I'll probably email you. If I email you, is that going to, so I guess I'm just going to say, I can do that, right? I can just be like, be sure to check your email. Email on Sunday to see which problem you're assigned. Yeah, okay. So, like, you'll get an email, and it'll be like, tomorrow you're expected to present this problem. What I might do is, I might just make a spreadsheet, and then just share the spreadsheet. Do I want to do that? You guys see any problem with that? If I just send you a spreadsheet and it has the problem that's assigned to everybody? It certainly cut down on the work on my end a little bit. I mean, it's... Yeah, I could upload it on Canvas and email it as well. I'm just thinking about it. I might change that. I don't know, but just regardless, on Sunday, just be sure to check your email. I'll probably try to work on Saturday afternoon and assign all the problems, or Friday, whatever I do it. And then I'll get it to you as soon as I can. Since we meet at 10 a.m. on Monday morning, I'll try to make sure that it's out by that time on Sunday. And I feel like as long as you have at least 12 hours notice, it's probably fine. Because That's the next thing to say, like, to best prepare. This is what you want to do. You want to go back and review all the mastering physics problems and make sure you understand how to do them. If you know how to do all of them, then no matter what I ask you, you should be able to do pretty well, I assume. I don't think the mastering physics problems are all that challenging, personally. I don't know what y'all think. I mean, I hope that after you've turned in this this lab manual homework that, like, I would assume that it kind of broadened like your understanding of some of the concepts and kind of reinforced some of those concepts by challenging you at a higher level. So I suspect when you go back and you look at the mastering physics problems and, like, go back over them, they're probably going to be pretty easy, right? Maybe I'm wrong. I don't think this should be very challenging, and I think that the biggest thing is just going to be, like, the problems will be pretty easy. It's just a question of, can you clearly explain everything? Can you clearly explain all the steps? And then if I, just understand that, like, I might ask questions during the exam that are slightly beyond the question itself. And if it's a really hard question, I might not judge you too harshly if you don't know the answer. But what I would judge you on is just your attempt. You know what I mean? I mean, just like today, like, this is a good example of, like, what we were doing today, where, like, we were talking about degrees of freedom, and I just asked you guys to just kind of guess. Like, you don't just, like, what's the reason why we... That's the kind of question I'm going to ask you. It'd just be this kind of open-ended question where, like, I'm not necessarily going to expect that you get either the right answer or the answer I'm looking for. I'm just going to expect that, you can use your brain and you can kind of reference something within physics to answer. Does that make sense? Like, less judging you on your ability to get additional questions right, and more just on how you're thinking about them, how you're approaching them. So. And I'm not going to ask you things that are really hard. It's going to be things that are, like, directly based on the problem. So I encourage you that when you do look back at your mastering physics problems, kind of just think deeply about them and think about, what could I ask? Let me give you an example, actually. That'll be a lot more clear. An example together. Sure. So just go to the mastering physics, you mean, and kind of, like, pull a problem up. Master P. Some of these 1B problems are really easy. So, I wonder if 10 minutes is going to be too much time. Okay. So this will be the last chapter that's on the test, basically, is 18. Okay. Just this one. All right, let's go back to the earlier chapters. Let's look at fluid stacks. There's one problem that was interesting. Kenny says, only one? All right. I picked this one back. The clock one, is that the one where the pendulum is, like, heated up and you want to figure out the change in time? Yeah, that's a good problem. We could do it that one is you could take the same thing, the same pendulum, and you could look at the way in which the temperature affects, like, the period of the pendulum, and then you could ask the question, what altitude could you put that pendulum at that temperature so that it would cancel out the effect of the temperature change? You know what I mean? Because the pendulums basically swing at different rates based on their altitude. So that would be a good question for, like, a final exam. Okay, it always starts on student data view, which I hate. I don't know why you'd ever want to look at that one, but... Okay, is this a good one? Oh, I remember this problem. We actually got questions about this problem because it was really vague. Okay. I can immediately think of questions that I could ask on this one. So the problem is an electrical short cuts off all power to a submersible diving vehicle when it's a distance of 34 meters below the surface of the ocean. The crew must push out a hatch of area 0.95 meters squared and weight 290 newtons to escape. And the question is, if the pressure inside is 1 atmosphere, what downward force must they exert on the hatch to open it? Now, at the end of the day, I think this problem ends up being pretty straightforward. What you have to do is you have to use the fact that they're 34 meters below the surface, which means there's going to be an additional pressure on their submersible. And I believe at 34 meters, it's something like 3 additional atmospheres of pressure, right? So the pressure at that depth is about 4 atmospheres. And you get that by doing density of water times G times this distance. Yeah. So it's about 3 extra atmospheres of pressure, roughly. So what you end up doing, it says the crew must push out a hatch of this area and this weight. If I remember correctly, I think this weight ends up being really negligible in the calculation, right? Is that right? You guys don't remember? But I think ultimately what you have to do is just take this area and multiply by the pressure. So it's like 3 atmospheres multiplied by this right here. And that gives you a force. And you could then subtract the weight if you want to. But I'm pretty sure, here, let's do a calculation real quick. Should really just put a link to this right here. I probably have a link somewhere in here. This thing to open. Well, that didn't work. Oh, where's the problem? It's in a different window, right? It's this one. There we go. Okay, so let's just check. So the additional pressure is given by pressure at the surface, which is 1.013 times 10 to the 5. Plus rho GH, so rho is 1,000 for water, times 9.8 for G, backspace, and then times 34 meters. So 4,500. Then it says the pressure inside the vessel is 1 atmosphere. So we subtract away from this 1.013 times 10 to the 5. So that gives us our pressure. And if we take that and we multiply by the area of the hatch, which is about 1, so 0.95, then this is the pressure, the force. This is the force now, because we did force times area. So this would be the force that you need to actually push open the hatch, right? And I'm pretty sure in terms of like what Mastering Physics is going to use here, that you can tell that if you subtract 290 newtons from that, the weight of the thing is not going to change the answer by enough. It's not even going to alter. It's only going to alter the 3rd digit right here. So I'm pretty sure the answer for this one is something like 3.1. We'll just do 3. I don't know how. I'm just going to say 3.2. Oh, let's do it like this. Let's write 3.2. 0, 0, 0, 0. See if that's enough to actually be within their threshold range. This is rounding error. So if instead we do 3, 1, 6. How about that one? Is it like that? No, it doesn't like that either. How exact does it need to be? So if we do 3, 1, 6, 5, 4, 0, and we subtract from that 290, what do we get? You get 3, 1, 6, 2, 5, 0. Does that one work? Oh, did I make a mistake when I did this? What is it saying? Oh, okay. It wants us to round to 2 significant figures. Wasn't the first number I did 2 significant figures? 3, 2. Does it want... would it prefer that I put this into, like... what's it called? Wait a minute. What's it saying? Okay, it actually didn't count me off for this one. They want me to put it in scientific... Yeah, that's what I thought. Okay. Now, how do you do scientific notation here? Do you just do, does it let you do stuff like this? Does that work? Is there like a special button for this? Like that? Oh. Yeah. I used to use WebAssign, and they would let you put in numbers like... Oh, cancel. Submit. that not two significant figures? I very much respect the fact that you guys have to deal with this. Yeah, I know. I know how it feels to be you. This is awful. I hate mastering physics so much. Wait, what's wrong? Check your writing. The final answer around it. This is two significant figures, right? Did I just do the calculation wrong? It's possible I did the calculation wrong, I guess. So what if the hatch is on the top? So if the hatch is on the top, we actually have to add 290, right? Do you then get 3? Well, it's still 3.2. So I don't. Did we make a mistake? Let's see. Electrical short cuts off power distance 34 meters. I mean, we're not losing any points, so it must be correct. It's just like they don't like the way that we've written it, right? 17. 290. Yeah, that's what it's saying. It's totally saying the wrong answer. This is the wrong answer, but okay, does it just not like the format? Let's try this again. 3.2. Is this normally what you do to do the scientific notation? It's like this. Okay, and this is here. There's a way to do 3.171 E5, which would be 3.2 E5. How else can we do it? We could do 32 E4 or something like that, I guess. We know it's not going to work. Do you think, is it 1.7? There's no way. That'd be hilarious. No, see, that's wrong. What about 3.16? Huh. How did you guys get this one right? This problem's awful. Electrical shortcuts off all power the distance of this below the surface. This area, yeah. You just cried. Oh, you just didn't get it right? You just get it wrong? Yeah, you subtract the weight. That's what we did. That's the number they got? Oh, did I plug in? Oh, it's seawater. That's what I did wrong. It's seawater. Sorry, I shouldn't have done this so quickly. I should have read it more carefully. Where did it go? So they're saying it's seawater. So if we do that, and we look up the... Well, and see the number that they have here. So how do I get the number they used in the book? 1029 is something I always see show up in the book. So let's use 1029 for the density of seawater, and let's try it again. Gotta tell you, if this is the good thing about doing this stuff on a test, by the way, is that I'm not gonna like worry about that kind of stuff. Where is the problem? It's in a different linear, right? Not that one. That one, right? Okay. So it would be 34 meters times 1030 times the height, which was... No, not the height. Gravity times 9.8. And then we take that, we multiply by 0.95. That was the area. And then we subtract from that the 290. Yeah, so it ends up being 3.3. Huh, interesting. What's funny is that, oops, not next, submit. Okay. I did this on purpose to remind you. I definitely didn't do any of this on purpose, but certainly a good thing to pull up because this addresses a lot of issues that might come up during a test. So, it does say ocean, you know, so that's my bad for not realizing that it might be seawater. It's a really good learning moment there. But yeah, again, on a test, I'd be more judging, you know, could you do this part, right? Like, if you got the density wrong here, it's no big deal. Because it's more about the process, right? I'm not gonna be really hard on you or anything like that about little things like that. Yeah, the ocean part. Okay, so what else could I ask in this case? You know, I might ask you something like suppose you went through your derivation here, and you get the answer, and then there's a lot of time left. Let's say, you know, like we have 10 minutes, and let's say you still have 5 minutes left over. At that point, what would I ask you? I actually had an idea of what I was going to ask you before, and then I've forgotten it now. I don't know. This is a really basic problem. It's hard to come up with something else to ask. Yeah, I was gonna say, like, what if the hash is on top? No, the hash is on top in this one, right? Because we subtracted it to get the right answer, even though it doesn't say it. Because we're pushing up and the hash is pushing down. So this would be hash on top. But the answer is, like, the answer is the same if you put it on top or bottom, right? Because you still get 3.3. It's just different to this to the second decimal place right here. Yeah, I don't know this problem. This might be one of the problems that I end up just not putting on the test. Because what I'll do is I'll go through all the problems. I'll come up with a set of 30 problems that I think are good. And if it's too simple, I'm probably not going to ask it, basically. But let's look at another one. What's another one here? I think a lot of these statics problems are going to be kind of boring. Yeah, it's like some of these problems are just so simple, unfortunately. No, not this one. There we go. These problems are so easy. Anyway, the clock. Well, so here's a problem. Like, normally I would love to, like, go over all these problems with you guys, but since we're doing an exam on it, it kind of feels weird. The clock is from which chapter? Is it from 17? Okay. The one on heat transfer or temperature and heat? Probably heat transfer, right? No, it's probably this one. It is heat transfer, okay. Do you know what number it is? 9, okay. Oh god, that takes so long. All right. A particular pendulum clock keeps correct time at 20 degrees Celsius. The pendulum shaft is steel and its mass can be ignored compared to that bob. What is the fractional change in the length of the shaft? Well, this is really easy. You just do, like, something like delta L is equal to alpha for steel times the initial length times the change in temperature, right? So you can calculate what this is. And they want fractional, so you end up doing this divided down here. Oh, whoops, not that. Sorry, you're dividing this one down here. So you'd get that quantity. And then how many seconds per day will the clock gain? So what part of this did you guys want to talk about? Part C, how many seconds per day will the clock gain or lose? So so 13. This says fractional expansion. Is that what we want? Yeah, this makes me want to go to the textbook just to make sure. Use 13? Okay. 13 times 10 to the negative 6? going to be right here. Yeah, the book has 1.2. I don't know. We'll use 1.2. I think usually using the value from the book is kind of generally better. 13 and 12 is pretty close anyway, so I bet you get the same answer regardless. Or at least close to it. Okay, so the temperature change was 5 degrees, right? 20 to 5. Yeah. So it's going to get shorter. So if we do 1.2 times 10 to the negative 5, this is just over degrees Celsius, I believe, times delta T. So the change in temperature is from 20 to 15. So it's 15 degrees Celsius minus 20 degrees Celsius. This is 5 times... Oh, this is pretty easy to do, right? So it's going to be 6D. So if this goes over 1, this becomes negative 6. 60 times 10 to the negative 6 will be 6 times 10 to the negative 5, I think. Yeah, Andrew, I mean, I'll go in order of whoever's here. Should you all show up at 10 o'clock? I mean, probably not, but there's 15 of you, so probably, like, we'll get through, like, 6 in the first hour, 6 in the second hour, and then the third hour will just be whatever's left. So if you're in the first hour of people, you probably show up at between 10 and 11. But here's the thing, like, if someone doesn't show up, I'm just going to go to the next person, right? So just kind of be around, I suppose, and hang out in this voice channel, and I'll pop in and ask for you for the next person or something like that. It's going to be a little weird the first time. What's your last name? Andrew Elia, right? So you're probably going to be one of the first people that goes. So you could probably show up, but let me get around 10 o'clock or something like that. I'll probably give more instructions in the email I send out about like when you should be there and stuff like that. But like if we start the class and the first person on my list isn't there, I'm going to go to the next person on the list. And if that person's not there, I might just be like, all right, who's ready? You know what I mean? And I might just take whoever's available. So if you're looking to get it done soon, probably show up soon. If you end up being busy and you want to just come later, come later. I mean, I think we can just kind of play it by ear in that regard, right? Okay, so this is negative, right? Negative 6 times 10 to the negative 5. I'm wondering when you put this answer in here, if it's supposed to be negative. I don't know, let's see. So if you do negative 6, I seriously have to do this each time, huh? Nope, not like that. 6 times 10 to the negative 5. Is he going to like that it's negative? Probably doesn't like that it's negative, right? What? Oh, does this say absolute value or something? Is this what it shows up on your screen too? This, like... I have to refresh it? Oh, okay. Oh, weird. Okay, well, there you have it. So it does say absolute value. I see that now. You're right. Okay, cool. So that's that. How many seconds per day will the clock gain or lose at 50 degrees Celsius? Okay. So what equation do you need for that? You need the period of the pendulum, right? So I guess we could use the length here. So we need to know seconds gain or loss per day. Seconds per day. So the period of the pendulum would be this. We don't know what the length is, but we want to know That's what we know, is that the change in length is this. So we could think that this would be like, here, let's do this. This would be the period at 20 degrees Celsius would be this, and then the period at 15 degrees Celsius, whoops. The period at 15 degrees Celsius would be this, right? But this quantity, L naught minus delta L, would be equal to L naught minus 6 times 10 to the negative 5. So this would be equal to L naught times 1 minus 6 times 10 to the negative 5. That's basically what L naught minus delta L is, right? And 1 minus 6 times 10 to the negative 5 is going to be really close to 1, but not exactly that. No, that's not right, is it? So it's 9.999 e negative 1. Oh. Here, let's do standard. So it's there we go. So it's that number right there. Okay, all this stuff is junk, right? It's really just this. So 0.99, here you wrote it down so I can. So this is basically L naught times 0.99994. So then the period at 15 degrees Celsius, the period is the time that it takes for it to tick once, is going to be the square root of L naught so now we know the period is shorter, right? Everybody agree with that? The period is shorter, which means if the period, for example, was 1 second, our new clock is going to tick at a rate of a little less than, it'll take a little less time for it to tick a second, basically. Does that make sense? So if we fix this to be 1 second, then this is going to be whatever the square root of 0.9999. I'm just kind of using numbers to get an understanding of what's going on. So if we do 0.9, okay, we've got it. So, oh no, I didn't mean to do that. So 0.99994, we take the square root of that. So that is going to be that number, whatever, 0.9. This is how much shorter a second is going to be for the other clock, right? So this clock is going to be something like, 0.9999 whatever. But that's going to be the same thing as a second, basically, in a way. So the difference between these two, let's look at the problem again. How does it say it? How many seconds per day will the clock gain or lose? Seconds per day it's going to gain or lose. Right, it's almost nothing, but in a day is significant. So then what you have to do is you need to multiply that difference between these two numbers times 24 hours, basically, right? I think this is what you had. It's okay. This is just me almost just guessing. This feels like the right thing to do, is to take this difference and then multiply by, I think, by 24 hours in a day, which is 86,400 seconds. Does that seem right to y'all? It's the difference in time, right? I think that's right. So if we do that, We don't actually know what the length of the pendulum is, do we? I gotta look back at this and make sure that I'm not wrong about this. A particular pendulum clock keeps correct time, whatever that means, at 20 degrees Celsius. The pendulum shaft is steel and its mass can be, okay, correct time. Oh, okay, I have to read the problem. I'm such an idiot. A pendulum clock is designed to tick off 1 second on each side to swipe. Okay, it is 1 second. So, okay, this was correct. This assumption was correct, actually, even though it's actually written in the problem. Okay, so I feel a lot more confident about this, basically. So whatever this is. So we have to do... when y'all did this problem, did you solve for the length? Yeah, you probably solved for the length, right? Because we can't just do a ratio. Yeah. Yeah, we have to actually solve for the length, don't we? Okay. So the length is going to be equal to t squared, which is 1 second, divided by 4 pi squared times g, I believe. The answer is going to be something like 24.9, right? So it's 1 times 9.8 divided by 4 divided by pi divided by pi. Yeah. Oh, I was close. 24.8. So 0.248. We need this to, like, a lot of accuracy, don't we? I mean, what I'm going to probably do is just not round at all. 2482369. I'm not even going to round to that. And this is going to be in meters. So now we have to plug it into this equation. For the final equation we get right here, this is going to be 1 second minus. There's a way easier way to do this, actually. Because from this equation, you could factor out t at 20 degrees Celsius. And that would be equal to 1 minus the ratio of t at 15 versus t at 20. Right? That's correct, isn't it? But the ratio of t at 15 to t at 20 is this over this, which is really just the square. It's 1 minus the square root of 0.99994. This saves us from the problem of, this is 1 second per second. This is a really silly ratio, but you need to do it because otherwise this doesn't make any sense. 86,400 seconds per day. Okay, well, did what I do make sense here? This can actually allow you to not use this, basically. Not like it wouldn't work. It's just like I'm worried about the rounding when I know that this rounding is perfectly accurate here. So this should work. So we take so it's 86400 times 1 minus the square root of 0.99994. Watch this still not be right. So it's 2.6 seconds. Is that the answer? How much accuracy do they want on this one? So this answer was given with 3 digits. So it's 2.59 seconds. It's a good problem. It'll take 2.6. Okay, that's good to know. See, the real question would be, what altitude can you take it to, right? So that it still ticks 1 second every second. That'd be fun to do. Because gravity varies with height, right? And it gets weaker. So if the gravity got weaker by exactly the same amount, then it would still tick at 1 second, which would be kind of cool. But anyway, that would be an example of something I might ask during the test, to be like, what happens if you took this same thing to a higher altitude? Would it make it closer to the right time? Would it make it farther away from the right time? And if you didn't get the answer right, it'd be whatever. It'd just be like, how do you think about it? If that makes any sense. Okay, well now I can't put this one on the exam since we went through the whole thing on video, but that's probably good. I don't think this was a problem you guys were looking forward to doing on the test, considering how many people wanted to ask about it. But it's a good problem, right? You have any questions? No? Are there other problems or just general concepts you want to talk about before we stop today? Are there any other problems that you guys found particularly challenging? What I could do is, instead of actually solving it, we could just talk about how to solve it. Even though that's hard for me. It's hard for me not to just solve the problems, because I like solving problems. But are there any other problems from the last few weeks that stand out to you that you want to discuss? Just keep in mind, if you have a solution that you've already written down, make sure it's all in your own writing. Make sure you understand all the steps, because if there's even one step that you can't explain, that is definitely going to affect you. So just make sure you understand all the steps. I have office hours multiple times this week, so if there's anything you want to talk about, feel free. But yeah, let's use this time now. If there's any other things that you want to. I see someone typing, so I'm gonna let them finish. Are y'all happy the Lakers won last night? It's been a long time. The city was wild. Yeah, man. Did you guys go out and celebrate? So many fireworks. A lot of people at the Staples Center. When's the last time they won? Was it like 2009? 2010, okay. 2010 was the first year that was it 2010? Can't remember if I moved here in 2010 or 2011. But in the 2000s, they won so many championships. The Kobe Shaq era. And then, yeah, lately, they've just been so bad until LeBron got here. We were in 5th grade. It was a long time ago. Well, maybe they'll win again next year. Just not a lot of competition. The Nuggets team was pretty good, though. I thought the Clippers would be better. The East just seems really bad, though. Although, I feel like the Heat would have had a chance to take it to 7 if they hadn't been so injured. They had a pretty good team. All right, well, do you guys have any other questions? I'll probably stop the recording for now. But if you